All right. I got referred to this when in a class. So let's see here. This is probably what I want.
Let's have a look at one of these tests that they have, that they apply to see if a number is prime or not. Well, we're going to use a fact that I have mentioned before when talking about primes. We're going to use Fermat's little theorem. It's a theorem about prime numbers, and what it says is if you have a number which I'll call A, and I'm going to raise it to a power prime number, so let's call P prime, and I subtract the original number, then I say that this is divisible by B. There we go. So if a number is prime, that's always true for whatever number A you pick. So let's do an example of this. Let's pick a prime. We know 5 is a prime. It is, isn't it? Yes, okay. So 5 is a prime. So let's use that, and we'll pick something. Well, let's see, 1 to the power 5. That's going to be easy. 1 to the power 5 minus 1 equals 0. Is it divisible by 5? Yes, we say 0 is divisible by 5. What about 2? 2 to the power 5 minus 2, so you get 30. Hey, that's divisible by 5 as well. Let's just finish it off. 3 to the power 5 minus 3, that's 240. So these all divisible by 5. 4 to the power 5 minus 4, divisible by 5 again. What about 5? Yeah, well, I think this one's a bit more obvious, so that's divisible by 5 too. And that's always going to be true if the number is prime. This is what Fermat proved in the 17th century. This is absolutely true for all primes. Let's try another number. I'll try another number with you. I'm going to try the number 341. Does that pass my test? 2 to the power 341 minus 2. That's my test. Now that's going to be a really large number. Computers can have methods that make this easier, so that's going to be a really large number. I'm not going to write that down. Huge number, but I can tell you now that this number is divisible by the number we're testing. It was 341. Thumbs up. Yeah, great. So it's passed the test. Let's try another one. Let's try another test. Let's do it with 3 then. We do this. 3 to the power 341 minus 3. Is this divisible? And this is where it fails the test. So this one is not divisible. Now, if it's not divisible, that tells me it's a composite number. There only needs to be one exception. It's very easy to fail this test. The more you pass, the more evidence you are that you are prime. And if you fail at all, then you are a composite number. Only composite numbers fail. If you have a composite number and it passes the test here, this number 2, in this case, is called a Fermat liar. Ooh, it's not really prime, it's lying. It tells me it's prime and it's not. Naughty. This number here, 3, which actually shows that it was composite after all, is called a Fermat witness. The innocent bystander. He goes into a witness protection program in case 2 comes and chases it after him. Yeah. Brady, you ask a good question though. What would happen if there was a number that was composite that passed every test up to the size of the number? Is it possible? Yes, it is. There are numbers that will pass this test for every test you apply. Those are called Carmichael numbers. They have a name. The first Carmichael number is 561. So what that means is 2 to the power 561 minus 2 is divisible. 3 to the 561 minus 3, that passes the test. So does 4, and all the way down to 560 to 500 to the power 561, and it passes the test each time.
Must be prime.
Must be prime. Must be prime. Unfortunately, it's not. 561 is equal to 3 by 11 by 17.
Those are cool numbers.
Those are really cool numbers, and there are infinitely many Carmichael numbers. The third Carmichael number is mathematician's favourite, 1729. Nice.
Lovely.
Lovely. Now, What do you reckon, Bray? Do you think this is a good test or not?
Well, till you told me about Carmichael numbers, I thought it was a good test. Now I think it's almost useless if you're looking for perfection. Well, it is useless.
Yeah, well, it's not perfect. You're absolutely right. So, if you checked all numbers less than 25 billion, the number of numbers that would fail the test, if you used A was 2, all right. If A was 2, the number of numbers that fail that particular version of the test is 2,183 out of 25 billion. That's just using 2. So only a small fraction fail this test, or give you things that you don't want, tell you that you have a prime when you don't have a prime. And you can apply other numbers anyway, so to pass this test is actually quite a high bar.
So it is a good test.
So it's a fairly good test. Now there are other tests though, there are better tests that use pretty much the same idea, almost exactly the same idea, so if you understood that, you'll understand the other tests as well. There's one called the Bailey PSW test. Pretty much uses the same idea as that. Actually uses 2 tests in conjunction, so you have to pass them both. Yes, if you pass that test, you're probably a prime. In fact, they have found no counterexample. So anything that passes the test so far has actually been a prime. There's been no sneaky composite numbers, no counterexample to this, and they've checked large numbers for this. If you do find a counterexample, you find a cheeky composite number that passes the test, the authors originally offered a prize. You could win $30. $30 could be yours now. Don't worry. Since then, the amount of the prize, it's gone up since then. You can now win over $600. $620, in fact. Think of that. Think of that. Think what you could do with that money. Ooh, you could buy yourself a choc ice every day. Every day for a year, twice on Sundays. 2002, they published, or mathematicians published, a new method to test for primes. And finally, they found a fast way that was 100%. This is now one of the latest things.
My perfect business.
Yeah, that was a great video. Is this the next one?
We're going to do a prime, because we do love we're going to do a silly one today. We're going to talk about a special number. We like doing videos about special numbers, and we're going to do a prime, because we do love our...
Yeah, that was really cool. Mostly self-explanatory.
Let's have a look at...
Not sure that there needs to be a ways to practice this. Let me see here. I wish there was a playlist so I can just jump to that next one that they were talking about. Fermat liar. $61. Then they go through there are infinitely many carmichael numbers. It always tricks the test. bit. It's just one time. Failing that, it's not prime. This shows. Alright, I think I understand what it's talking about. Let's see here. I want to be able to find the next ones. That was just teased here. I can't just click on these. Looks like
Things.
time videos. Maybe had the playlist about this. Quite a few playlists. Okay. Alright, just 2 on primes. Here's the next one.
That's not Minhaj. What are you doing in the office, man?
This looks related to witness numbers. Most evil number. Okay. Sexy primes. This was the class that sparked this YouTube video. It's encryption and primes. So Mersenne prime, which is of the form 2 to the exponent minus 1 is a prime. This is what we just watched. A foolproof test for primes. And 513 and 563. 383 is cool. Oh. RSA 129 sounds cryptography related. Okay, I was looking for.
We're going to do a silly. Yeah, we're doing.
Foolproof test.
2002, mathematicians published a new method to test for primes, and finally they found a fast way that was 100%. This is now one of the latest things. So this is called the AKS test. And it's pretty much a very similar idea to what we did with the Fermat little theorem. It's very similar to that. And the test is, if you've got a number p, and we are going to do this. I'll take x minus 1 to the power p, and then we're going to subtract x to the p minus 1. All right. So it's a polynomial. I'll show you an example in a second. If all coefficients are divisible by p, then p is prime. And if they're not, it's composite. It's 100% this test. I'll show you an example. Let's take x minus 1 cubed. Yeah, let's do that. X minus 1 cubed.
So 3 is the number we're testing.
Yeah, 3 is the number we're testing. We know it's a prime, don't we? But we're going to test it. We're going to take x minus 1 cubed. So that's, to make it explicit, x minus 1 by x minus 1 by x minus 1. Okay. Multiply this out, you get a polynomial called x cubed minus 3x squared 3x minus 1. That's what you get. Now you're subtracting the x cubed, I'm told to do that, and you're, what's that, adding on the 1. So these disappear. It says these numbers are divisible by 3. If it is divisible by 3, 3 is the number we're testing, then it is a prime. If it's not divisible by 3, it is not a prime. And that's a 100% test. So this was really important. This was huge news when they published this. 2002 they published it. And it was huge news because it was a fast test as well. Or it could be made into a fast test. There's a little thing they do just to make it a bit faster, because it does get quite difficult. These polynomials get quite nasty. Just to make it a little bit faster, what they did is x minus a to the power of p minus x to the p minus a. So a is a number, like we had before. And they said this was equal to p lots of something plus, there you go, a little x minus r minus 1 multiplied by something. So that's not quite the same, that's a little bit different. This was actually faster to work with, it makes a faster calculation. And for this version, you need to test a few candidates for A here, you just test a few. And if it passes that test, then you can determine that P, which is what we're trying to work out, try and work that out, you can find it's prime or not. Mathematics is done all day, every day. New mathematics is coming out all the time. And only, well, I say recently, 12 years ago, they finally solved the problem. It is still faster to do a Fermat test. It's still faster to do this, but this is not outrageously slow anymore. It doesn't take us to the end of the universe anymore. So we can actually run this test. It's slower than the Fermat test, but 100% true.
Oh, wow. That is cool. Don't have too much time. I will, there's one more I wanted to watch, which is, yeah, this one, I think. 9 minutes.
So I've got a very big number to show you today, used by NatWest Bank, so that you can send them your secret bank details. It starts 2, 3, 4, 5, 3, 6, 7, 6, 2, 8, 0, 6, 1, 6, 0, 1, 6, 5, 8, 0, 6, 5, 0, 0, 6, 2, 1, 7, 0, 8, 4, 0, 6, 2, 8, 7, 7, 4, 1, 7. Did you get that, or do you want me to repeat it? So this number that we are reading out is 617 digits long. All banks have similar numbers when you want to send them your credit card details. This is not a secret number. In fact, your computer will download this number when it wants to send your credit card details. It's there to find. This is public. So this code that they use on the internet is called RSA. It's named after the 3 people who came up with it, who were Rivest, Shamir, Adelman. Shall I show you how it works? All right. Imagine if you had a secret that you wanted to send to the bank. So the bank provides you with a box, and it provides you with a key to lock the box. So you can put your secret inside, and you can lock it. And then you can send the secret to the bank. That's good, isn't it? But the problem is, if the bank is giving everyone one of these boxes and a key that goes with it, then that means that, well, one person could steal someone else's box and use the key to unlock it and read their secrets. That would be terrible. We can't do that. So what the banks do, same sort of idea, but instead of giving out keys, they give out padlocks. So they give everyone a box. You've got a secret, put it inside the box, lock it, not with a key, but with a padlock. It goes click, it snaps shut. Once it's locked and snapped shut, you don't have the padlock key. So you can't reverse it, you can't open it up. So if someone steals your box, they don't have the key either. They've got a padlock, but they don't have the key to open the padlock. The only person that does is the bank themselves. And it's a way to send secret messages without having to send out the keys. It's easy to lock the code, but it's hard to unlock the code. First of all, I have to explain this with the smallest example I can, and then I'll show you why we use that massive number. Let's say you're the bank, and you give out two numbers. They're public, so everyone can know them. They're not secret numbers. I'm going to choose the number 3 and the number 10. The bank also has a secret number. The bank's secret number, for now, you don't know what it is. No one knows what that is. Only the bank knows what that secret number is. I had a very bad breakfast this morning, so I'm going to send the message, bad chef. The first thing you do, if you have a message like that, is to turn the letters into numbers. That's quite simple. A is 1, B is 2, and Z is 26. Simple stuff. C is 3, D is 4. Now I'm going to turn it into a code, and I'm going to use the number 3. Now there are some codes that would just add 3, or there are some codes that would multiply by 3. What we're going to do is raise to the power 3. So we're going to cube these numbers here. Let's do that. So I get 2 cubed, which is 8, 1 cubed, which is 1, 5 cubed is 125, and 6 cubed, 216. The final step is to use the second number, the number 10. I'm going to divide by 10, and I'm going to look at the remainder. So if I take something like 512, when I divide by 10, there'll be 51 tens, and then 2 left over. That's just 2, 5 here, 1 and 4. And that's your code, and that's what you would send. The bank, or the person who's going to decode this message, has a secret number. Now the secret number is, in this example, is going to be 3. There's a formula to work out the secret number. I'm going to gloss over that for a second, but I'm going to show you what to do next, to decode the message. This is my code. I'll write it out again. I'm going to do the same thing I did before. This time I'm going to use my secret number. It doesn't have to be the same as 3, but it just happens to be the same as the 3 we used before. But never mind, it doesn't have to be. But I'm going to cube again. So I cube these numbers. We do like we did before. We divide by 10 and find the remainder. And then the decoder will turn that into letters, which is B, and he gets the message back again, bad chef. Now that's just a taste of how it works. That's the process that your computer does every time you buy something on Amazon or eBay. One of the important numbers in this code was this 10. Now this 10 was made by multiplying two prime numbers together. 2 times 5 are prime numbers, multiply them together and you get 10. Now that massive number that I showed you that NatWest uses, it's the same idea. It's 2 massive prime numbers multiplied together. That's what it is. If you want to work out the decode key, the secret key, you need to know the original prime numbers. Now the only way a spy, someone who wants to break the code, could work out the original prime numbers is to take that massive number and factorize it, turn it back, break it up into the original 2 prime numbers. This is really hard. So hard that it's impractical to break with modern technology. The massive number I showed you was a 2048-bit number. That means it's about 2 to the power 2048. Now, about a decade ago, we did manage to break 512-bit numbers. We were able to take that number and factorize it into its original primes. A few years ago, a team of academics managed to break a 768-bit number. It took this team of academics with all their resources 2 years to break a 768-bit key. And they said that to break what we use now, which is about 1024, would take thousands of times longer. But given the speed of technology, they reckon that this sort of code, 1024-bit, could be broken within a few years, they said. They said that a few years ago. So this should now start to be replaced. Gmail still uses this, but this should be replaced. And as you can see, NatWest have done that, other banks have done that. They are now using 2048-bit number, which again would take computers, and I mean even with a proper attack, big computers, it would still take them thousands of years to factorize that number into its original prime numbers. Now, hidden in the details for this code is a mathematical fact that was worked out in the 17th century by Pierre de Fermat. He's famous for Fermat's last theorem. Well, this was Fermat's little theorem. If I take a number, a whole number, an integer, any number, call it x, I'm going to raise it to a power, and it's going to be a prime number, so p for prime. I'm going to raise it to a power, and I'm going to take away x. This is a multiple of p, the prime number. Let me do an example. What I mean is, if you took a number like 4, and then I took a prime number like 5, and then I take away 4, I would get 4 to the power 5, which is 1024. Take away 4, which is 1020, and that is a multiple of 5, but that would be guaranteed. You're guaranteed to have a multiple of 5. Now, you can imagine that in the 17th century, when Fermat came up with this fact, that people said, well, very nice mathematical fact, but that's pretty useless. Well, what use are you going to have for that? And then suddenly the internet comes along, and it's massively useful. In fact, our whole modern world depends on this fact. So to use this code, the public key has 2 numbers. I've shown you the massively long one that NatWest uses. The other number that they need, which is the power that you have to raise, that is not as big. That is 65,537. Quite a big number. When you compare it to the second number, it's small.
If you're in the mood for even more about banks and really big numbers, then check out my latest video from the Chemistry Channel periodic videos, where we've been inside the Bank of England gold bullion vault, where they have a couple of £100 billion worth of gold lying around. That's not something you see every day. The link is here on the screen and below the video.
All right. Huh. Okay. Is that the same as this RSA 129? No. Okay. Well, I think that's it for this one. Kind of short on time.